Hello students, welcome back to JCE Connect series of lectures. So in this particular lecture, let us take some of the examples how the sections are being classified, that is examples on a section classification. And in previous lecture we have seen how the sections are being classified. There I explained various things. This graph I explained. So there is a moment versus the curvature, and this represents the plastic sections and compact sections, then the semi-compact section and the slender sections. So this graph I explained in the previous lecture, and based on this graph how the sections are being classified, let us see by taking some of the examples. And here just I have taken some of the examples. Here classify the following sections, that is take ISLB 400 at 56.9 kg per meter, and another example I have taken ISHV 400 at 77.4 kg per meter, and one more ISHV 200 at 37.3 kg per meter, and one angle section I have taken as 100 by 100 by 6 at 9.2 kg per meter. So let us see each one of this in which category these sections will lie. We'll check it. Let us take the first one, that is ISLB 400 at 56.9 kg per meter. So first I am taking ISLB 400 at 56.9 kg per meter. So we'll check this particular section, that is ISLB Indian Standard Light Beam 400 at 56.9 kg per meter, whether this section is a plastic or a compact or a semi-compact or a slender. So let us check this one, and for that one, so let us draw the I section. This is I beam, like this. It's I beam. I beam, and this represents width of the channel, and this is depth of the section, width of the flange. This is width of the flange, depth of the section, and this is thickness of web and thickness of flange. Then as per the code, if we want to classify the sections, so this is the figure given here based on these figures, this figure. So look at this figure. So here I section rolled beams and columns. So this I section can be used as a beam as well as can be column, and whether this section, that is a given section or the providing section, whether it is a plastic or a compact or a semi-compact, you can decide based on taking the individual elements of the section. Individual element, flange is one element and web is one element. If you take individually, then if you have to check the ratios of the those elements, that is ratios means width to thickness and depth to thickness, if you take it, and those ratios are being given here in this table number 2, that is limiting width to thickness ratios. And once you calculate the ratios, then you have to check that ratios with the given ratios in table number 2 of IS 800 2007. So with respect to this figure, so here individual element to be taken. So here the B is the outstand width of the flange given here, and the effective depth of the web section as a D given. Now we have to calculate this outstand flange width as well as the depth of the section. So here B represents outstand flange width and the D represents the effective depth of the web. Okay, so let us mark that one in this figure. Mark here. So first I'll mark the center line of this I section. This is the center line, and this represent the B. Then the ID will be from the leaving the root fillet of the root radius. This one D, effective D. Okay, now from referring steel table you have to take the properties of the section. So refer steel table, take the properties of the section. You have to refer the steel table, ISLB 400. So refer ISLB 400 here. So 400, ISLB 400 at 56.9 kg per meter. Then take all the properties. Depth is 400, width of the flange is 165, then thickness of flange is 12.5, thickness of web is 8. Then in this figure, so here R1 represents the root radius here, R1, and this is the radius at toe, and it is the radius at heel. This is given here, radius at toe, radius at root, and radius at toe. So this is the root and this is the toe, and those radius also required here. Then let us take the properties of the section. Properties of the section from steel table. So that is depth of the section, that is H is 400, H is 400. Then width of the flange is 165 mm. Then thickness of flange will be 12.5 mm, and the thickness of web will be 8 mm. Then the root radius R1 here, in this particular root radius R1 here. Okay, R1 will be 16 mm. Okay, now you have to calculate the ratios, that is to classify these sections you need to calculate the ratios. So here compression element is given, here ratios you need to calculate. Look at this table, you need to calculate the ratios for the rolled section. You have to calculate the width to thickness of the flange, and again depth to thickness of web. So you have to calculate the ratios. So let us calculate the ratios. For that, outstand of flange, that is outstand of flange that is B equal to this one. This will be the outstand of flange B. We have to take this B, that will be BF by 2. Then how much you will get? 165 by 2, you will get 82.5 mm. Similarly, depth of web, T, this one from here to here, depth of web, that will be H minus 2 times of thickness of flange plus R1. So look at this. This is the H minus 2 times of thickness of flange minus 2 times of R1. Here root radius, here root radius you have to take. You have to take the effective depth of the web. Okay. So what you get here? 400 minus 2 times of 12.5 plus 16, you will get 343 mm. Then after calculating the outstand of flange width and the depth of web, this is as per the code. So to be considered the section as a compact or a plastic or a semi-compact, you need to calculate these individual element width and depth. Now you have to calculate the ratio. The first ratio to calculate B by T, width to thickness ratio. So we have obtained 82.5 divided by 12.5, so we get 6.6. Okay, and one more ratio, depth to web. So depth is 343 and ratio thickness is 8, we get 42.88. So this is the ratio we have obtained. Now these ratios you have to compare with the given limits, that is, this is the limits given in a code limiting width to thickness ratios. So the first is B by TF. If the section to be class 1, then it should be less than or equal to 9.4 epsilon. Okay, now we have to compare this one. First one 6.6, so which is less than 9.4 epsilon, where epsilon is given here. Look at this table. Epsilon is given here, root of 250 divided by Fy. So this section we are considering the yield stress of this section. Here also we are considering Fy is 250 Newton per millimeter square, and you can calculate epsilon equal to root of 250 by Fy, you will get 1. Okay, so when the ratio is calculated which is less than 9.4 epsilon, then we can write flange is plastic. The flange element is plastic. So we have to calculate, separate the element wise. So flange element acts as a plastic element. Now again you have to compare the depth to thickness ratios. So depth to thickness ratios you have to compare. So here the depth to thickness ratio is given as 84 epsilon. In our case it is a 42.88, again which is less than 84 epsilon. Hence the web is plastic. So both the elements of the section, means flange element as well as the web element, both are acting as a plastic in this case. Therefore the section is plastic section. So like this you have to classify the section. So both are plastic here, hence the section is plastic. And suppose if one element is a plastic and other one is a semi-plastic, or a or you can call it as one is a plastic, other is a compact, then you have to take the least one. Least means here it is given, just I'll read it, just look at this one. Different elements of a cross section can be in different classes. Means if suppose if flange could be in plastic and web is in a compact, in that case, that is in such cases the section is classified based on the least favorable classification, whichever is the least one. If we take the plastic as a highest, and plastic next to plastic is a compact, next to compact is a semi-compact, next to semi-compact is a cylinder, we have to take the least favorable classification. In this case, whatever the example we have taken, both are lying in a plastic, hence the section is plastic. If one is a plastic and other one is a semi-compact, then we have to take the least favorable condition, that is semi-compact, hence the section being classified as a semi-compact section. But in this case, both are lying in a plastic condition, that is hence the section is plastic. Let us take one more example and see. Second one, if we take ISHB 400 at 77.4 kg per meter. So again refer steel table for this section. This is also I section, same I section only. You just take this I section and take all the properties from the steel table. So I'll take properties from the steel table, that is depth, height of the section is 400 mm, then the width of the flange as a 250 mm, then the thickness of flange, that is 12.7 mm, then thickness of web 9.1 mm, then you have to take the root radius as 14 mm. So these all you take from the steel table. Then calculate epsilon, again same, 250 by Fy, you will get to 1, 250 by 250, you will get to 1. Then calculate outstand width of flange, that is B equal to Bf by 2. This one, outstand width of flange. To classify the section, we need to take this outstand width of the flange, then the ratios. So outstand width of the flange Bf by 2, then when you take 250 by 2, you'll get to 125 mm. Then depth of web, we get depth of web as D equal to H minus 2 into thickness of flange plus R1. So when you substitute the thickness of flange and R1, you will be getting 346.6 mm. Now calculate the ratio. The first ratio I calculate width to thickness of flange. First I'll take the flange element. The flange element I'm taking 125 by 12.7. You will be getting 9.84. Again this 9.84 you have to compare with the table 2 of IS 800 2007. Let us compare this one. B by TF I am taken, and class 1 is a plastic section, 9.4 epsilon up to 9.4 epsilon is a plastic section, and if it crosses 9.4, that is more than 9.4 and less than 10.5 is a compact section. But in our case it has crossed 9.4, hence I can write which is less than 10.5 epsilon. So 10.5 epsilon means it is a compact section. Therefore flange element is compact. Okay, next ratio, that is depth to thickness of web, D by TW. So D we are having 346.6 divided by thickness of web is 9.1, so you will get 38.08. Again you have to compare this depth to thickness ratio from this one. So look at this depth to thickness ratio. Here is 84 epsilon, 105 epsilon and 126 epsilon. But in our case it is 38. So which is less than 84 epsilon. Therefore web element is plastic. Web element is plastic. So in this case, these two elements are behaves differently. One element behaves as a compact and one element behaves as a plastic. So what the code says, if the different elements are behaving differently or lying in different classes. So as I said earlier, look at this one. Different elements of a cross section can be in different classes. Suppose if they are lying in different classes, in such cases the section is classified on the least favorable classification. I'll repeat, different elements of a cross section can be in different classes. In such cases the section is classified based on the least favorable classifications. So in this one, which is the least favorable classification? Least one. So if I consider plastic is the highest one and the compact next to plastic is a compact, so this is the least favorable. Okay, hence therefore the section is compact. So section becomes compact. Okay, I hope you understood this one. So let us take one more example. The third one, if I take ISHB 200 at 37.3 kg per meter. So again for this section ISHB 200 at 37.3 kg per meter, take all the properties from the steel table. So I'll be taking the width of the flange 200 mm, then the depth will be 200, then the thickness of flange will be 9 mm. These all are taking from the steel table. Then thickness of web 6.1, then the root radius you take it is a 9 mm. Then you calculate outstand flange width, that is B will be BF by 2 you have to take, that is 200 by 2, you will get 100 mm. Then depth of web, that is D will be H minus 2 times of thickness of flange plus R1 root radius. So I explained about this one how it comes. So if you deduct that one, you will be getting how much you will get, 200 minus 2 times of thickness of flange as 9 plus 9, you will be getting 164 mm. Then calculate the ratios. So ratios of different elements. The first element I'll consider the flange element, then the ratio of width to thickness of flange. So width to thickness is 100 divided by thickness of flange will be 9, you will be getting 11.11. So when I compare this ratio with the table, the limiting value given in table, so look at this table. So in this case I am getting more than 10.5 but less than 15.7. So more than 10.5, less than 15.7. Now I can write this is more than 10.5 epsilon but less than 15.7 epsilon. Hence I can write here the flange element is semi-compact. It is semi-compact. Up to the 10.5 is a compact. If it crosses 10.5, then the element will be lying in semi-compact range. It's 15.7 up to, okay. Then ratio of depth to thickness of web. So 164 divided by 6.1, what do you get? 26.8. So again it will be less than 84 epsilon. Therefore web element is plastic element. Web element is plastic. So in this case, again, one element, that is a flange element, lying in a semi-compact, and the web element lying in a plastic. But you have to take the least one, that is least favorable condition. Therefore the section is semi-compact. Like this you have to classify the section. So once you know the classification of section, then the design bending moment can be easily calculated further. Okay, so let us take that angle section, fourth one, and let us check in which classification it lies. So I'll take the angle section, that is ISA 100 by 100 by 100 by 6 mm. Again, for this also refer steel table, take all the properties. So this is I section. So as for the code, this will be the width and this will be the depth. If you take this one, so look at here, in this one single angle I section, this is the width and this is the depth given. Okay, again this will be the thickness. Okay, now referring steel table, you will be getting the gross area as 1167 millimeter square. Then the width, that is the angle leg width 100 mm. Then the depth 100 mm. Then the thickness you will be getting 6 mm. Then again you can calculate epsilon root 250 by Fi. Again Fi is the yield stress. Then it can be coming as 1. Because Fi is 250. 250 by 250 is 1. Root of 1 is 1. Then again calculate the ratio as usual. Calculate the ratios. So one ratio is a B by T. So B is 100 by 6. You will be getting 16.66. So 16.66. So again you refer the table, limiting value for the angle section. So here it is mentioned here. Look at here, angle compression due to bending. Angles are been using, and it is a compression due to bending. Both criteria should be satisfied. Then width to thickness ratios. Then the limiting values are been given here. 9.4 epsilon, 10.5 epsilon and 15.7 epsilon. In our case it is more than 15.7. More than 15.7 epsilon. So what the code says, read here. So look at this. So here the cross sections in which the element buckle locally even before reaching the yield stress, then the width to thickness ratios of the plate element shall be greater than the specified, that is class 3. If the element ratios coming more than the specified given in class 3, in such cases the effective section for design shall be calculated either by following the provisions. So here this section is greater than the limits given in table number 2, that is 15.7 is greater than 16.66 is greater than 15.7. Hence the section, or I can say sorry, hence the element, therefore the this one, no, before one more issue I have to calculate, that is a d by t, then 100 by 6 equal to 16.66. Again this is also greater than 15.7 epsilon. Hence the section is slender one. The section is slender. You have to classify the section as a slender because it has crossed the limits given in code. The limits are given in a code. It has crossed. Here for angle section compression, it is given d by t. See, 9, it has crossed, so both it is lying 15.7 up to 15.7 is which section? Semi compact section up to 15.7. if it is crossing 15.7, so it is slender sections. Hence this angle section, whatever the angle section was given, so this is lying in class 4, that is slender section. So like this you have to classify the sections based on the width to thickness ratios and depth to thickness ratios, because the different elements will be lying in different classification, that is different class, and based on the least favorable classification you have to decide whether the section is plastic, compact or